On the afternoon of January 31st, 2000, 88 people were flying at 31,000 feet over the Pacific Ocean. At the back of their MD-83 sits the horizontal stabilizer, the flight surface that dictates whether the nose points up or down. At 9 minutes past 4, the captain keyed his radio to report a problem. He spoke in the flat, procedural tone of a pilot troubleshooting a localized failure. The trim motor was running, he said, but the stabilizer was frozen in place. The aircraft was locked in a fatal trajectory, but the reason was entirely silent. The wings had not suffered a structural fracture. There was no hidden metallurgical defect in the steel. The crew had made no error. The control column was frozen because of a single number buried in a maintenance schedule. Over the course of a decade, that number had drifted upward, one routine approval at a time, until it destroyed a finger-sized bronze component the entire airplane depended on. When engineers design an aircraft, they build in backups to prevent a single component from bringing down the plane. Here, that physical redundancy was replaced with the assumption of procedural perfection. Finding the physical evidence of that failure required recovering the wreckage from the seabed. The first pieces brought to the surface included the flight recorders, giving investigators raw data of the crew's inputs and the chaotic final movements. But the explanation for those movements lay in another recovered part, a mechanical assembly called a jackscrew. The recovered hardware showed no signs of a sudden, catastrophic break. Instead, the physical evidence bore the deep, uniform scars of a critical machine left completely alone to grind itself away. Pitch control on the MD-80 series is managed by the horizontal stabilizer, the small wing-like structure mounted at the very top of the tail. To tilt that entire surface, the aircraft uses a jackscrew assembly. A threaded steel rod turns slowly inside a nut. As the screw rotates, the nut travels up or down the threads, pivoting the stabilizer along with it. The 22-inch screw is made of case-hardened steel. The component traveling along it, called an acme nut, is cast from a copper alloy of aluminum, nickel, and bronze. That material mismatch is deliberate. The bronze alloy is soft. Engineers design the nut to be the sacrificial wear point of the system, because a nut is cheap to replace, and a hardened steel screw is not. The designers at McDonnell Douglas reasoned that the nut had two independent sets of threads, and that routine inspections would catch any wear before both sets gave way. Based on that logic, they installed no mechanical backup. If the nut stripped completely, there was nothing beneath it to catch the screw. The entire safety architecture of the tail relied on two simple acts. The threads had to be greased, and the wear had to be measured. Mechanics tracked that degradation using an end play check. By loading the screw in opposite directions, they could measure the space between the wearing threads on a dial gauge, tracking the gap in thousandths of an inch. This graph illustrates how the maintenance intervals shifted over time. When the aircraft entered service, the jackscrew required grease every 500 flight hours. By the late 1990s, that interval had been stretched to roughly 2,500 hours. The end clay checks followed the same trajectory. Originally performed during heavy maintenance, the intervals expanded until a plane could fly more than 9,500 hours between measurements, ignoring the manufacturer's absolute limit of 7,200. The investigators looking into these extensions recorded a specific procedural failure. The intervals had been expanded without any supporting empirical data. No physical testing proved the grease could actually survive that long. During the final service before the accident, mechanics completed the lubrication in about an hour in the dark. The manufacturer estimated the procedure required 4 hours. A few pumps from a grease gun left the long steel threads nearly dry. The official paperwork showed an aircraft in compliance, but the numbers on the page no longer reflected the physical reality inside the tail. Months before the accident, the maintenance system nearly intervened. During an inspection, a mechanic read the end play gauge and, following procedure, ordered the assembly replaced due to excessive wear. The recorded measurement was 40 thousandths of an inch. That result sat firmly outside the allowable safety limits. But the assembly was not replaced. The airline used its own non-standard, uncalibrated fixtures to secure the mechanism for the test. Armed with imprecise tools, they ran the check again and again, 5 times over. Eventually, the gauge returned a reading of 33 thousandths of an inch, just inside the legal limit. The failing score was discarded, and the passing score was kept. An uncalibrated tool had produced a comfortable lie. The warning was crossed out, and a dangerously degraded component was cleared to fly again. Which brings the timeline back to the flight deck over the Pacific. When the pilots first noticed the stabilizer would not move normally, they began working through their manuals, trying to understand the nature of the jam. What they felt through the controls was not a locked brake. It was the last 10% of the acme nut's heavily worn threads violently binding against the steel screw. The crew activated the primary trim system one last time. The mechanical force broke the jam, and those final threads sheared off entirely. The cockpit voice recorder captured the physical collapse, 4 distinct thumps, followed 17 seconds later by a massive tear, as the long steel screw bypassed the stripped nut completely. Without the jack screw holding it in place, aerodynamic pressure slammed the horizontal stabilizer into an extreme nose-down limit. The aircraft pitched over violently, forcing the plane to roll inverted. For 81 seconds, the two pilots hung upside down, pulling on the control columns with up to 140 pounds of force. But they were fighting the physics of an airframe where the primary pitch control linkage simply no longer existed. The definitive proof of this sequence was pulled from the ocean floor. The physical state of the recovered jackscrew assembly left no room for debate regarding how the failure occurred. The bronze threads of the acme nut had physically peeled off and were found tightly wrapped around the severely galled steel screw. It was the physical signature of years of metal grinding directly against metal where grease should have been. This chart compares the engineering assumption with the forensic reality. The original designers calculated that a properly lubricated nut would lose roughly 1/1000th of an inch of thread per 1,000 flight hours. Laboratory analysis of the recovered parts established the actual rate. The metal was disappearing at 12/1000ths of an inch for every 1,000 hours of flight. The threads were being obliterated 12 times faster than the design allowed. When an engineering architecture is built without a mechanical failsafe, the maintenance schedule becomes the structural integrity of the aircraft. By stripping away that oversight, a decade of procedural shortcuts ensured an ordinary bronze nut became a fatal point of failure.